Hello everyone, my name is Dongwei, and this is my presentation for InterSpeech paper on Speech SimCLR, combining contrastive and reconstruction objective for self-supervised speech representation learning. First, let's go into the introduction. Self-supervised learning is gaining popularity recently. On one hand, deep learning relies heavily on large amounts of high-quality labeled data, but obtaining labeled data is very costly and time-consuming. On the other hand, self-supervised learning attempts to extract knowledge from unlabeled data can potentially discover representations that capture the underlying structure of such data, which helps with the performance and conversion speed of downstream tasks. In the area of speech, researchers propose many self-supervised pretraining algorithms. Wave2Vect extracts representation from data using a contrastive loss that requires a true future audio sample to be distinguished from negative samples. Some following work extend this approach and learn vector quantized representations of audio data using a future 10-step prediction task with the help of BERT. Autoregressive predictive coding is a reconstruction objective that got inspiration from language model in NLP and tries to predict unseen future frames based on past frames. The idea is further extended in another future work, which also added the objective of past frame prediction. Some other reconstruction methods were motivated by NLP. Most of them applied BERT-style masks on input feature representations and adopted reconstruction objective for representation learning. It is worth pointing out that some of the above methods used augmentation during the training of unsupervised models. These augmentations help to make learned representations more robust and improve the performance of downstream tasks. Also employed augmentation methods, SimCLR, a feature representation work from Image is a framework for contrastive learning of visual representations. It learns representations by maximizing the agreement between differently augmented views of the same image via contrastive loss in the latent space. SimCLR improved considerably over previous supervised, semi-supervised, and transfer learning methods that capture specifically designed architectures in terms of top-1 accuracy for ImageNet. The best results obtained by it can also match its supervised counterparts. Inspired by the recent success of SimCLR, we propose Speech SimCLR, a new self-supervised objective for speech representation learning. Speech SimCLR first conducts augmentation on raw speech and its spectrogram. It then learns speech representation by maximizing agreement between differently augmented sample via a contrastive loss in the latent space. Contrastive and reconstruction objectives help speech representation learning in different ways. Recent work claimed that self-supervised representation can be further improved by combining contrastive and reconstruction objectives. We also tested this theory in our work. So in our work, we combine contrastive objective and reconstruction objective. As for model structure, an illustration of Speech SimCLR is provided in Figure 1. So first, we applied augmentation on speech. For augmentation to a specific speech task, we try to use these methods that would bring variation to input speech, but would not affect the final result of downstream tasks. For speech representation recognition and speech emotion recognition, we applied random pitch shift, speed perturbation, root reverberation, and additive noise to the original waveform. Time masking and frequency masking are also applied to spectrogram. All of our augmentations are conducted using the open source WaveAugment tool. The stochastic data augmentation module transforms any given data, example X, randomly to two correlated views of the same example xi and xj. After that, a neural network-based encoder F extracts representation vectors from augmented data examples, hi equals f xi and hj equals f xj. These encoder outputs are the representations that would be used in downstream tasks. Transformer-based models have been proven to be very effective for various speech tasks. So we need transformer layers as we use transformer layers as the building blocks for the encoder parts of Speech SimCLR. After encoder, we applied average pooling on the encoder output and used a projection head to map it to the space where contrastive loss is applied. Following SimCLR, we also used a nonlinear MLP with one hidden layer as the projection head. Specifically, the output of the projection head is Zi equals G average pooling Hi equals for contrastive learning to work, distributed training is usually required to get a large batch size. During the training of Speech SimCLR, positive pairs are computed in the same device. And if batch norm is used, the model can exploit local information leakage to improve the prediction accuracy because the batch norm mean and variance are aggregated locally per device. So we replaced all batch norm in our model to layer norm, as suggested in SimCLR paper. So for a local device, so the positive samples will always be in the same device as the negative samples, like in the GPU card. So if and the batch norm are calculated locally. So if we use batch norm, then the information leakage will be inevitable. Now comes to the experiments. As shown in Figure 1, Speech SimCLR achieved competitive accuracy on IEMO compared to previous work using other features. OpenAudio contains MACI-ENDE, which contains 408 hours of speech, LibreSpeech, which contains 960 hours, and ESC-US, which contains 347 hours of speech. There are previous work that used self-supervised pretraining with it to boost the performance of IEMO. Despite smaller pretraining data size, Speech SimCLR is able to match its performance when used alone and exceeds its performance when combined with reconstruction loss. As for ASR tasks, we used two methods. We use Speech SimCLR as a feature extractor, and we try to use it as directly in fine-tuning. For the results using Speech SimCLR as a feature extractor is shown in Figure 2. We compared our work with other work that used a similar setup. On LibreSpeech test clean, Speech SimCLR achieved lower error rates than other pretraining methods, even when more fine-tuning data is used, like in the VQ Wave2Vect work. PER with Speech SimCLR on Timid is only worse than one former work, which used a pool of LibreSpeech TD release and WSJ Corpora as pretraining data. It is also worth mentioning that FBank is considered to be a worse feature than fMLR in Terra. With the help of reconstruction objective, Speech SimCLR is able to achieve better results than Terra. Despite that, as for using Speech SimCLR for fine-tuning, we conducted similar experiments and showed the results in Table 3. For LibreSpeech, as shown in Table 3, Speech SimCLR achieved lower error rates compared to most other pretraining methods. More importantly, Speech SimCLR still provides benefits to downstream tasks, even when similar augmentation is used during fine-tuning. Our results is worse than YuanFuDao 2.0, but we would like to point out the import feature for YuanFuDao 2.0 is raw waveform points, while the import feature of our work is F-bank. The extra parameters from CNN feature structure and the calculation gave YuanFuDao an advantage. Also, the model size of YuanFuDao 2.0 base contains 95 million parameters, which is much larger than the model we used. The model we use contains only about 30 million parameters. It's a standard transformer structure with 12 layers of encoder and 6 layers of decoder. And other factors like quantization also contribute to the superior performance of YuanFuDao 2.0. We believe the findings in this work and YuanFuDao 2.0 are complementary and can be applied together to get better speech representation learning. The YuanFuDao 2.0 is mostly used for contrastive learning. We can apply augmentations on raw waveform and spectrograms and use the sign objective function as YuanFuDao 2.0. And we believe this would bring benefits to representation learning. And in order to study the impact of augmentation on different target problems, we retrained a number of Speech SimCLR models with liberal speech trickling 100 set and discarding one augmentation at a time. For fine-tuning datasets, apart from timid and IMOCAP, we also added DiDi, a challenging speech recognition dataset containing reverberation and dynamic background noise to see how augmentation in Speech SimCLR would affect downstream tasks in different recording conditions. The training for both timid and DiDi is done using the MLP configuration in PyTorch Coding to make training faster. The accuracies of Table 4 show that no augmentation is dispensable, and the best results are achieved when all augmentations are present. For individual augmentations, adaptive noise and speech probation are generally the most crucial ones for speech recognition. Root vibration is not so useful for timid and IMOCAP, but it is really important for DiDi. We believe it's because the DiDi dataset is also artificially contaminated with room vibration. As for emotion recognition, pitch shift and frequency mask are the most important augmentations. We believe it's because these two augmentations have the biggest influence on pitch estimation, which is closely related to emotion. We also evaluated the effects of batch size and training epochs for Speech SimCLR. These experiments are conducted with the whole 960 hours of liberal speech as pretraining data, and the liberal speech trickling 100 as fine-tuning data, as shown in Figure 2. Using larger batch size and training for more epochs does bring benefits to downstream tasks. I believe it's pretty much the same for all pretraining, fine-tuning paradigm. Especially there are lots of work that pointed this out. I believe it's first learned in Robert's paper, and after that, pretty much all pretraining work tries pretty much all pretraining work has got benefits from larger batch size and more training epochs. We also find that when the number of training epochs is small, for example, for only 50 epochs, larger batch size have a significant advantage over the smaller ones. With more training steps or epochs, the gaps between different batch size decrease or disappear. The finding here echoes with the conclusion from original SimCLR paper and shows that larger batch sizes are beneficial for contrastive learning because it provides more negative samples. Training for longer also have the same effect because with more epochs, it is natural to see that more negative samples will be seen by the network, which makes the task of distinguishing positive sample and negative sample harder. So this way, and it will make the network learn more about the downstream task and help the performance of downstream tasks. That's all for my presentation. Thank you.